Hello! I'm Professor Von Schmohawk, and welcome to YU. In the previous lecture, we saw that when Gauss-Jordan elimination is used to transform a matrix that represents a dependent system of linear equations, the result will be an independent system of fewer equations from which the solution set can be easily determined. Although the planes corresponding to this new system may be different than the original planes, the solution set of the system will always be the same. In this lecture, we will look at one example from the previous lecture and see how the planes were transformed step by step from a system of 3 planes representing 3 equations, each containing 3 variables, to a system of 2 planes representing 2 equations, each containing only 2 variables. In this example, no 2 equations were multiples of each other. However, each one is in fact a linear combination of the other 2, and so all 3 equations are dependent, although it would be very difficult to tell this just by looking at the equations. Now let's represent this system of equations as a matrix, and see what happens when we transform the matrix to reduced row echelon form. We start the process of Gauss-Jordan elimination by changing the first row's leading entry to a 1, using a scale operation to multiply row 1 by 1/4. As we saw in the lecture entitled A Geometrical View of Gauss-Jordan Elimination, scale operations have no effect on the planes. We then change the entry below to a 0, using a pivot to add -4 times row 1 to row 2. Since the pivot operation adds a multiple of row 1 to row 2, it causes plane 2 to rotate around its line of intersection with plane 1. And since the x coefficient in row 2 has changed to 0, plane 2 has become parallel to the x-axis. We then change the entry below that to a 0, using a pivot to add -16 times row 1 to row 3. Since this pivot operation adds a multiple of row 1 to row 3, it causes plane 3 to rotate around its line of intersection with plane 1. And since the x coefficient in row 3 has changed to 0, like plane 2, plane 3 has also become parallel to the x-axis. Since both planes 2 and 3 rotated around the same line of intersection to become parallel to the x-axis, both planes are now identical. You may notice that matrix rows 2 and 3 are now multiples of each other. Row 2 is 4/5 times row 3, and row 3 is 5/4 times row 2. We now move to the second column, changing the second row's leading entry to a 1, using a scale operation to multiply row 2 by 1/16. We then change the entry below that to a 0, using a pivot to add -20 times row 2 to row 3. But since rows 2 and 3 were multiples of each other, the multiplier we picked for row 2 zeroed every entry in row 3. As a result, row 3 no longer describes a plane, and now we have a system consisting of only 2 planes. For this matrix to be in reduced row echelon form, each leading entry must be the only non-zero entry in its column. Although the leading entry for row 1 is the only non-zero entry in its column, the leading entry of row 2 is not. Therefore, we must change the entry above row 2's leading entry to a 0. We do this with another pivot, adding 1 times row 2 to row 1. Since this pivot added a multiple of row 2 to row 1, it causes plane 1 to rotate around its line of intersection with plane 2. And since the y coefficient in row 1 has changed to 0, plane 1 is now parallel to the y-axis. Since both leading entries in the matrix are now the only non-zero entry in their columns, this matrix is in reduced row echelon form. Converting this matrix back into equations, eliminating the terms with 0 coefficients, eliminating the coefficients of 1, and the equation 0 equals 0, we now have an equivalent system of 2 independent equations. So Gauss-Jordan elimination has created an equivalent independent system of 2 linear equations. The solutions of the system correspond to the infinite number of points contained in the intersection line of the 2 planes which correspond to these equations. And once again, this infinite solution set can be written in parametric form. So, although this system initially contained 3 distinct planes, because all 3 planes shared a common line of intersection, when Gauss-Jordan elimination caused planes 2 and 3 to rotate around this line to become parallel to the x-axis, planes 2 and 3 became identical. As the process continued, since rows 2 and 3 both described identical planes and were therefore multiples of each other, row 3 became 0, eliminating one dependent equation that described one of the identical planes. This resulted in an equivalent independent system composed of 2 intersecting planes. Finally, Gauss-Jordan elimination caused plane 1 to rotate around the intersection line to become parallel to the y-axis. The infinite solution set of this system, represented graphically by the intersection line, can now be written in parametric form, as we will see in the next lecture.